Swayam Prabha. Digital India. Educated India.
In this session, I will now discuss the various techniques by which a digital satellite data can be converted into information of interest. So, let us discuss image classification and analysis. In image classification, an analyst attempts to classify features in an image by using the elements of visual interpretation to identify homogeneous groups of pixels that represent various features of land cover classes of interest. In digital image classification, the analyst uses the spectral information represented by the digital number in one or more spectral bands and attempts to classify each individual pixel based on this spectral information. This type of classification is termed as spectral recognition. In either of the case, that is visual or digital, the object is to assign all pixels in the image to particular classes or themes. The resulting classified image is comprised of a mosaic of pixels, each of which belong to a particular theme and is essentially a thematic map of the original image. Before we proceed to the classification, let us look at what are the different types of class of information. Well, these can be categorized into two classes, information classes and spectral classes. Information classes are those categories of interest that the analyst is actually trying to identify in the image, such as different types of crops, different forest types or tree species, different geological units or rock type, etc. In spectral classes, the analyst tries to identify groups of pixels that are uniform or near similar with respect to their brightness values in the different spectral channels of the data. The objective is to match the spectral classes in the data to the information classes of interest. However, it is rare that there is one-to-one match between these two types of classes. Many a times, it is found that 2 to 3 spectral classes merge to form one information class, while some classes may not be of any particular interest. It is the analyst's job to decide on the utility of the different spectral classes and their correspondence to useful information classes. Well, the common classification procedures can be broken down into two broad subdivisions based on the method used, that is supervised classification and unsupervised classification. So, let us have a brief look at these two broad classes of classification techniques which are available. First of all, supervised classification. In a supervised classification, the analyst defines or identifies in the image homogeneous representative samples of different surface cover types or information classes of interest. These samples are referred as training areas. The selection of appropriate training areas is based on the analyst's familiarity with the geographical area and the knowledge of the actual surface cover types present in the image. Thus, the analyst is supervising the categorization of a set of specific classes. The numerical information in all spectral bands of the pixels comprising these areas are used to train the computer to recognize spectrally similar areas for each class. The computer uses special programs or algorithms to determine the numerical signatures for each training class. Once the computer has determined the signatures of each training class, each pixel in the image is compared to these signatures and labeled as the class to it closely resembles digitally. Thus, in a supervised classification, the analyst first identifies the information class based on which it determines the spectral classes which represent them. Now, let us have a brief look at unsupervised classification. In essence, it is the reverse of supervised classification process. Spectral classes are grouped first based solely on the numerical information in the data and are then matched by the analyst to information classes as far as possible. The programs called clustering algorithms are used to determine the natural groupings or structures in the data. Usually, the analyst specifies how many groups or clusters are to be looked in the area. In addition to specifying the desired number of classes, the analyst may also specify parameters related to the separation distance amongst the clusters and the variation within each cluster. The final result of this iterative clustering process may result in some clusters that the analyst would like to subsequently combine, or that some classes may have to be broken down. Each of these require a further iteration of the clustering algorithm. Thus, unsupervised classification is not completely without human intervention. However, it does not start with a predetermined set of classes as in supervised classification procedure. Now, let us have a detailed discussion on supervised classification. Unsupervised classification would be taken in the next session. So, in order to carry out supervised classification, the analyst may have to adopt a well defined procedure in so as to achieve a satisfactory classification of information. The important aspects of conducting a rigorous and systematic supervised classification of remote sensing data are as follows. First, selection of an appropriate classification scheme. Second, selection of representative areas as training sites. Third, extraction of training data statistics. Fourth, testing of training data for separability in order to identify the best possible combinations of band for classification. Selection of an appropriate classification algorithm, classification of image into appropriate defined classes, and finally, evaluation of classification accuracy. So, first of all, let us look at the classification scheme. Basically, a classification scheme is nothing but it defines the hierarchy of information from a broad class to a detailed level. With this premise, there are classification schemes that have been developed so that they can be readily incorporated as meaningful land use and land cover data as obtained by interpreting remote sensing data. Some of the important classification schemes are USGS Survey Land Use Land Cover Classification Scheme, or in short it is also referred to as USGS LULC classification scheme. The next is Michigan classification scheme, and the third is Covered-in Wetland classification scheme. It may be noted that the last two are specific classification scheme wherein a specific information has been taken into consideration. That is, in Michigan classification scheme, the primary information class is urban related, and thus the classification scheme pays more or devotes more attention to the different types of urban units which may be there, which could be identified. In covered in wetland classification scheme, as the name suggests, it probably tries to look at the various information classes that could be there in the wetland regions. So, we can say that the first classification scheme, that is the USGS LULC classification scheme, is a one which tries to take into consideration different types of information classes. The information classes have been initially defined for Landsat MSS, but fine tuned for better satellite resolution. By and large, there are 4 levels which are there. The first 2 levels are probably well suited for remote sensing data analysis. The third and the fourth level of USGS survey land use land cover classification scheme are more suited when one uses aerial photographs for interpretation of information classes. So, let us see in USGS LULC classification scheme, at level 1 there are 9 basic information classes such as urban or built up land, agricultural land, range land, forest land, water, wetland, barren land, tundra and perennial snow and ice. Well, if one is interested to have more detailed information, then probably level 2 information classes can be taken up. For example, in the urban or built up area, this can be further subdivided into 7 broad detailed classes such as residential, commercial and services, industrial, transportation, communication and services, industrial and commercial complexes, mixed urban and built up land, other urban and built up land. Similarly, the other broad classes as defined at level 1, they can be broken up into detailed information classes. For example, agricultural land can be further subdivided into 4 detailed information classes, rangeland into 3, forest into 3, water into 4 detailed classes, wetland into 2, barren land can be broken up into 7 detailed classes, tundra region could be broken up into 4 detailed classes, while perennial snow and ice could be done, can be categorized into 2 detailed classes which is there. Depending upon the type of information required by the analyst, the level of information classes can be selected and then the information from the satellite data can be acquired. Having decided the land use land cover classification scheme, then the next task is training site selection. Once a classification scheme has been adopted, the analyst may identify and select sites within the image that are representative of the land cover classes of interest. Training data should be of value if the environment from which they are obtained is relatively homogeneous. The image coordinates of these sites are identified and used to extract statistics from the multispectral data for each of these areas. For each feature class C, the mean value mu C I for each band of data and the variance covariance matrix V C are calculated in the similar manner as explained while extracting initial statistics of the satellite data. The success of supervised classification depends upon the training data used to identify different classes. Hence, selection of training data has to be done meticulously, keeping in mind each training data set has some specific characteristics. These characteristics are discussed below. First is number of pixels. It is an important characteristic regarding the number of pixels to be selected for each information class. However, there is no guideline available, yet in general the analyst must ensure that there are sufficient number of pixels selected. Next is size. The training sites identified on the image should be large enough to provide accurate and reliable information regarding the information class. However, it should not be too big, as large areas may include undesirable variation. The next characteristic is shape. It is not an important characteristic. However, regular shape of training areas selected provides ease in extracting the information from the satellite images. Then is location. Generally, information classes have small spectral variability. Thus, it is necessary that the training data should be so located that it accounts for different types of conditions within the image. It is desirable that the analyst undertakes a field visit to the desired location to clearly mark out the selected information. In case of inaccessible or mountainous regions, aerial photographs or maps can be provided the basis for accurate delineation of training areas. Then is number of training areas. The number of training areas depend upon the number of categories to be mapped, their diversity and the resources available for delineating training areas. In general, 5 to 10 training samples per class are selected in order to account for the spatial and spectral variability of information classes. Selection of multiple training areas is also desirable, as it may be possible that some training areas of a class may have to be discarded later on. It is found that it is usually better to define many small training fields than to have a few in number, but large training areas. Then is placement. The training area should be placed in such a way that it does not lie close to the edge of the boundary of the information class. The next characteristic to be considered is uniformity. This is one of the most critical and important characteristic of any training data for an information class. The training data collected must exhibit uniformity and homogeneity in the information. If the histogram displays one peak, that is unimodal frequency distribution for each spectral class, the training data is acceptable. If the display is multimodal distribution, then there is variability or mixing of information and hence must be discarded. Having had a look at the characteristic, now we have to look at the sequence by virtue of which the training data can be selected. So, let us look at the idealized sequence for selecting training data. In order to select training data, no fixed or well defined procedures can be laid out. However, as a guideline, the key steps in decision and evaluation can be enumerated as follows. First, collect information including maps and aerial photographs of the area under study. If any previous study has been carried out, then acquire the necessary documents, maps and reports. Second is conduct field trips to acquire first hand knowledge to selective and representative areas in the study area. The field trips must coincide with the date and time of data acquisition. If not possible, then it should be at the same time of the year. The third step is to conduct preliminary examination of the digital data in order to make an assessment of the quality of the image. The fourth step is to identify prospective training areas. These locations may be defined with respect to some easily identifiable objects on the image. Further, the same may be identified on the map and the aerial photographs if readily available. After this, extract the training data areas from the digital image. For each information class, display and inspect the frequency histogram for all the classes. In case of multimodal frequency distribution, identify the training areas which are responsible for the same and discard them. Thereafter, compute the training data statistics in the form of minimum and maximum value, mean, standard deviation, variance, covariance matrix. Now, ascertain the separability of the information classes using feature selection. In this particular slide, one can see the manner in which the histograms depict unimodal nature, thereby suggesting that the training data statistics which have been extracted or identified are homogeneous in nature. Once the training data has been systematically collected from each band for each class of interest, a judgment must be made to determine those bands that are most effective in discriminating each class from all others. Well, this process is commonly called as feature selection. The goal is to delete from the analysis those bands of data that provide only redundant spectral information. In this way, the dimensionality, that is the number of bands to be processed in the data set, may be reduced. This process also minimizes the cost of digital image classification, but hopefully not the accuracy. When we are to look at the separability, we find that there are many statistical separability measures which are available. First is city block distance, second is Euclidean distance, third is annual separation, fourth is normalized city block distance, fifth is Mahalanobis distance, sixth is divergence, seventh is transform divergence, eighth is Bhattacharya's distance, and ninth is Jeffrey Matsushita distance. Out of these, probably the separability measures as defined at serial number 7 or at 8 are very commonly used by the analyst. So, now let us look at each of these separability measures one by one. City block distance, commonly known as Manhattan distance or boxcar distance, is basically a separability measure to represent the distance between 2 points in a city road grid. It examines the absolute differences between and the coordinates of two objects A and B, and hence also known as absolute value distance. Euclidean distance is an popular measure of finding distance between 2 points or objects on the basis of Pythagoras theorem. The normalized city block measure that is better than the city block distance in the sense that it is proportional to the separation of the class means and inversely proportional to their standard deviations. If the means are equal, however, it will be 0 regardless of the class variances, which does not make sense for a statistical classifier based on probabilities. Angular separation is a similarity measure than a distance. It represents the cosine angle between two objects. Higher values of angular separation indicate close similarity. However, all of these measures do not account for the overlap in class distance, due to variation and thus not good measures of separability in case of remote sensing data. For this reason, probability based measures have also been defined. Feature selection may involve both statistical and or graphical analysis to determine the degree of between class separability in the remote sensor training data. Combinations of bands are normally ranked according to their potential ability to discriminate each class from all other using n bands at a time. Statistical methods of feature selections are used to quantitatively select the subset of bands or features that provides the greatest degree of statistical separability between two classes C and D. The basic problem of spectral pattern recognition is that given a spectral distribution of data in n bands of remotely sensed data, find a discrimination technique that will allow separation of the major land cover categories with a minimum of error and minimum number of bands. Generally, the more bands analyzed in a classification, the greater the cost and perhaps the greater the amount of redundant spectral information being used. This problem is demonstrated diagrammatically using just two bands of data, one band of data and two classes in the figure, wherein what we find is that there are two classes, their distribution is depicted, and what we find is that there is a overlap between the two classes which is there. Now, how do we interpret the overlap which is there? Examining the histograms in the figure, it suggests that there is a substantial overlap between classes 1 and 2 in band 1. When there is an overlap, any decision rule that could use to separate or distinguish between two classes must be concerned with two types of error. First, a pixel may be assigned to a class to which it does not belong, that is an error of commission. The second is a pixel is not assigned to its appropriate class, that is an error of omission. The goal is to select an optimum subset of bands and apply appropriate classification technique to minimize both types of errors in the classification process. If the training data for each band are normally distributed as suggested in the figure, it is possible to use either a divergence or transform divergence equation to identify the optimum subset of bands to use in the classification procedure. Divergence was one of the first measures of statistical separability used in machine processing of remote sensing data and is still widely used as a method of feature selection. It addresses the basic problem of deciding what is the best Q band subset of n bands for use in the supervised classification procedure. The number of combinations C of n bands taken Q at a time is expressed by the equation C is equal to factorial n divided by factorial q within brackets n minus q factorial. Thus, if there are 6 thematic mapper bands and we are interested in 3 best bands to use in the classification, this results in 20 combinations that must be evaluated. If the best 2 bands combinations were desired, it would be necessary to evaluate if 15 possible combinations. Divergence is computed using the mean and the covariance matrices of the class statistics collected in the training phase of the supervised classification. The degree of divergence or separability between two classes C and D expressed as diverge C D is computed according to the formula as given below, where diverge C D is equal to 0.5 trace of the matrix defined by V c minus V d multiplied by the inverse of the variance matrix of class C minus the inverse of the variance matrix of class D plus 0.5 the trace of the matrix which is V c inverse plus V d inverse multiplied by the matrix M c minus M d multiplied by M c minus M d transpose, where T r is the trace of the matrix, that is the sum of the diagonal elements. V c and V d are the covariance matrices of the two classes C and D, and M c and M d are the mean vectors. It should be remembered that the size of the covariance matrices V c and V d is a function of the number of bands used in the training process. That is, if 6 bands were trained upon, both V c and V d would be matrices of 6 by 6 in dimension. Divergence in this case would be used to identify the statistical separability between the two training classes using 6 bands of training data. However, this is not the usual goal of applying divergence. What we actually want to know is the optimum subset of Q bands. For example, if Q is equal to 3, what subset of 3 bands provides the best separation between the two classes? But what about the case where there are more than 2 classes? In this instance, the most common solution is to compute the average divergence. This involves computing the average of all the possible pairs of classes of C and D, while holding the subset of bands Q as constant. Then another subset of bands Q is selected for the M classes and analyzed. The subset of features or bands having the maximum average divergence may be the superior set of bands to be used in the classification algorithms. Well, this can be expressed as diverge is equal to summation of C is equal to 1 to m minus 1 double summation of C plus 1 to m minus 1 divergence of between the two classes divided by capital C, where capital C is the number of band combinations that we have. Using this, the band subset Q with the highest average divergence would be selected as the most appropriate set of bands for classifying the M classes. Kumar and Silva in 1977 suggested that it is possible to take the divergence logic one step ahead and compute transform divergence, which can be expressed as divergence is equal to 2000 within brackets 1 raised to the exponential power of divergence between two classes C and D divided by 8. Well, this statistics gives an exponentially decreasing weightage to increasing distances between the classes. It would also scale the divergence values to lie between 0 and 2000. There is no need to compute the divergence using all 6 bands, since this represents the totality of the data set. It is useful, however, to calculate divergence with individual channels such as Q is equal to 1, since a single channel might adequately discriminate between all of the classes of interest. The transform divergence values of 2000 suggest excellent between class separation. Above 1900 provides good separation and below 1700 is poor. There are other methods of feature selection also based on determining the separability between two classes at a time. For example, the Bhattacharya distance assumes that the two classes C and D are Gaussian in nature and that the means M c and M d and the covariances matrix V c and V d are available. So, Bhattacharya distance can be computed on the basis of the equation as given here, that is 1 by 8 difference between the mean matrices of class C and D multiplied by the variance covariance matrices of class C, the average of the two multiplied by M C minus M D raised to the power, that is the transpose, plus 1 by 2 log of the determinant of the average of the variance matrix of class C and D divided by the square of the determinant of V C and the square root of the determinant V D. To select the best Q bands, the combinations of bands from the original n bands in an M class problem, the Bhattacharya distance is calculated between each of the m minus 1 divided by 2 pairs of classes for each of the possible ways of choosing Q features from n dimensions. The best Q features are those dimensions whose sum of the Bhattacharya distance between the m minus 1 divided by 2 classes is highest. The JM distance, also called as the Jeffrey-Matsuda distance between a pair of probability distributions of spectral classes, can be defined as J I is equal to integral x under root of p x omega I whole square into dx. Well, this is seen to be a measure of the average distance between the two classes, class density functions. For normally distributed classes, this becomes JM distance for two classes I and j, this is equal to 2 within bracket 1 e raised to the power x. So, on the basis of this information, what we can now find out is the distance between the two classes. In JM distance, the value would range between 0 and 2. Then we come to the next step in image classification, and that is selecting the appropriate classification algorithm. Various supervised classification methods have been used to assign an unknown pixel to any one of the classes. The choice of a particular classifier or decision rule depends on the nature of the input data and the desired output. Parametric classification algorithms assume that the observed measurement vectors x c obtained for each class in each spectral band during the training phase of the supervised classification are Gaussian in nature, that is, they are normally distributed. Non-parametric classification algorithms make no such assumptions. Amongst the most frequently used classification algorithms are the minimum distance, parallelopiped and the maximum likelihood classifier. So, now let us look at each of the classifiers one by one. First is minimum distance to means classifier. It is one of the simplest and the most commonly used decision rule classifier. Here the analyst provides the mean vectors of each class in each band from the training data. To perform a minimum distance classification, the distance to each mean vector from each unknown pixel represented as BVIJK is computed. Using the Euclidean distance based on the Pythagorean theorem, the distance between the unknown pixel and the respective class center can be computed by the following relationship as shown. To whichever class the unknown point has the smallest distance, to that class the unknown pixel is assigned to. It can result in classification accuracies comparable to other more computationally intensive algorithms, such as the maximum likelihood algorithm. The next classifier is the parallelopiped classifier. This algorithm is based on simple and or Boolean logic. Training data statistics in n spectral bands are used in performing the classification. Brightness values of each pixel of the multispectral imagery are used to produce an n dimensional mean vector with mu ck being the mean value of the training data obtained for class C in band K out of m possible classes as defined previously. Sigma Ck is the standard deviation of the training data class C of band K out of the m possible classes. Using a 1 sigma standard deviation threshold, a parallelepiped algorithm decides BVIJK is in the class C if and only if mu Ck minus sigma Ck is greater than BVIJK, but is less than mu Ck plus sigma Ck, where C is equal to the number of classes and K is equal to the number of bands. Therefore, we can now define a low and high decision boundaries, where low would be equal to mu Ck minus sigma Ck and high Ck would be mu Ck plus sigma Ck. So, the parallelepiped algorithm can now be simplified that if BVIJK is greater than low Ck, but less than high Ck, these decision boundaries form an n dimensional parallelepiped in the feature space. If the pixel values lie between the low and the high thresholds of a class in all the n bands evaluated, it is assigned to that class. Otherwise, it is assigned to an unknown category. The next classifier is the maximum likelihood classifier. The classification strategies considered so far do not consider the variation that may be present in the spectral categories and also do not address the problem arising when spectral classes overlap. Such a situation arises frequently as one is interested in classifying those pixels that tend to be spectrally similar rather than those which are distinct enough to be easily and accurately classified by other classifiers. The essence of maximum likelihood classifier is to assign a pixel to that class which would maximize the likelihood of a correct classification based on the information available from the training data. It uses the training data to estimate the mean measurement vector MC for each class and the variance covariance matrix of each class C for band K. It decides that if X is in the class C, if and only if the probability of C is greater than the probability of I, where I is the possible number of classes. PC, that is the probability of the class C belonging to that particular class, can be defined by the relationship as expressed here, where it is minus 0.5 log E of the determinant of VC minus 0.5 multiplied by the product of the matrices defined by X minus MC transpose multiplied by the inverse of VC multiplied by the X minus MC matrix, and Pi is the probability of the class existing. Theoretically, Pi for each class is given equal weightage if no knowledge regarding the existence of the features on the ground is available. If the chance of a particular class existing is more than the others, then the user can define a set of priori probabilities for the features and the equation can be slightly modified, wherein what we do is we try to take into account the variation of the priori probability into the probability that has been computed previously. It has been observed that the use of priori probability helps in incorporating the effects of relief and other terrain characteristics. The disadvantage of this classifier is that it requires a large computer memory space and computing time, and yet sometimes may not produce the best results. After this, the next step which the analyst has to undertake is to make an assessment of the work or the classification which has been done. So, we now discuss classification accuracy assessment. Well, it can be said that no classification task using remote sensing data is complete till an assessment of accuracy is performed. The analyst and the user of a classified map would like to know as to how accurately the classes on the ground have been identified on the image. The term accuracy correlates to the correctness. In digital image processing, accuracy is a measure of agreement between the standard information at given location to the information at the same location on the classified image. Generally, the accuracy assessment is based on comparison of two maps, one based on the analysis of remote sensing data and the second based on the information derived from actual ground, also known as reference map. This reference map is often compiled from detailed information gathered from different sources and is thought to be more accurate than the map to be evaluated. The reference map consists of a network of discrete parcels, each designed by a single label. The simplest method of evaluation is to compare the two given maps with respect to areas assigned to each class or category. This yields a report to the areal extent of classes which agree to each other. The accuracy assessment is presented as an overall classification of map or as the site specific accuracy. Overall accuracy represents the overall accuracy between the two maps in terms of total area for each category. It does not take into account the agreement or disagreement between two maps at specific locations. The second form of accuracy measure is site specific accuracy, which is based upon detailed assessment of agreement between the two maps at specific locations. The standard form of reporting site specific accuracy is the error matrix, also known as the confusion matrix or the contingency table. An error matrix not only identifies the overall error for each category, but it also the misclassification of each category. An error matrix is essentially consisting of an n by n array, where n is the number of class or categories on the map reference. Here, the row on the matrix represents the true classes or the information on the reference map, while columns of the matrix represent the classes as identified on the classified map. This slide, as a matter of fact, shows the typical representation of an error matrix. The values in the last column gives the total number of true points per classes used for assessing the accuracy. Similarly, the total at the bottom of each column gives the information regarding the number of points or pixels per classes in the classified map. The diagonal elements of the error matrix indicate that the number of points or pixels correctly identified both on the reference and classified maps. The sum total of all these diagonal elements is entered at the right hand bottom element, the total, that is the total number of pixels correctly classified both in the reference and classified maps. The off diagonal elements of the error matrix provide information on the error of omission and commission respectively. The error of omissions are found in the upper half of the matrix for each class. It is computed by taking the sum of all the non-diagonal elements along each row and dividing it by the row total of that particular class. Well, in order to identify the accuracy, various accuracy indices have been developed. The most common one is the overall accuracy, where we find out the percentage of samples correctly classified. The next is the user accuracy, where the index of individual class accuracies computed from row total is expressed, while Producer accuracy is the index of the individual classes accuracy computed from the column total. Then we have other accuracy measures such as average accuracy, combined accuracy, kappa coefficient of agreement and weighted kappa. Well, we will have a look at all these accuracy indices with respect to the error matrix that is shown here. In this we find that a particular classification has been carried out for 6 types of land use and land cover. And what we find is that out of the total number of points which are available, that is 4,421 pixels, 4,081 pixels have been identified correctly on the classified map, and hence the overall accuracy is of the order of 92.3%. This statistics is useful, however, it does not report the confidence of the analyst. For this, in 95% one tail lower confidence limit test for a binomial distribution can be determined as shown in this particular equation, where p is equal to p dash minus 1.65 multiplied by the square root of p dash q divided by n plus 50 divided by n, where p is the overall accuracy at 95% confidence, p dash is the overall accuracy, q is 100 minus p dash and n is the sample size. If the value of p exceeds the defined criteria at the lower limit, then it is possible to accept this classification with 95% accuracy confidence limit. Normally, the defined criteria of confidence limit is set at 85%. For the given example here, the accuracy at the lower end is 91.6% and hence it is acceptable as classified map has met or exceeded the defined accuracy standards. This particular table shows the number of pixels omitted and the percentage error of omission and commission for all the 6 classes. For identifying the acceptability of the accuracy for individual classes, a two-tailed 95% confidence test for each category is undertaken by the relationship where p is equal to p dash plus minus 1.6 minus under root p dash q multiplied by q divided by n plus 50 by n, where p dash, q and n have been defined as defined earlier. On the basis of this, what we can find is that forest 1 class, as a matter of fact, fails to meet the accuracy test in terms of error of omission, as this value is less than 85% in the upper bound. Similarly, forest 2 category for percentage errors of commission fails for 95% confidence limit. Another coefficient of measurement of accuracy is the kappa coefficient. This particular procedure of determining the accuracy classification is highly dependent upon the training data samples used for classification and assessment of classification accuracy. In order to assess the agreement between the two maps, kappa, which is a measure of the difference between the observed agreement and between of the two maps and the agreement that may have been contributed solely by chance of matching the two maps. It attempts to provide a measure of agreement that is highlighted for chance, and it is expressed as follows: k is equal to observed accuracy minus expected accuracy divided by 1 minus the expected accuracy. The observed is the overall accuracy and the expected is an estimate of the chance agreement of the observed percentage correctness. The expected is computed by first taking the products of the rows and the column totals to estimate the number of pixels assigned to each element of the matrix, given that the pixels are assigned by chance to each class. So, here the computations for kappa is shown here, wherein on the further right hand side column, the total number of points which have been identified on the classified map and the row totals at the below which are on the reference map, these are taken to compute the expected agreement by chance, which is nothing but the sum total of the diagonal elements divided by total of all the elements, and on the basis of this we find that the kappa is equal to 0.904. That is, it says that the classification has achieved an accuracy that is 90% better than would have been expected from random assignment of pixels to the classes. In my next session, I would discuss on the unsupervised classification techniques. Thank you.